In this lecture, we're going to go over some synchronization examples. Hopefully this will provide more clarity because I know the last lecture was kind of dull. So, problems of synchronization. Synchronization problems are used to test proposed synchronization schemes. The three big ones are the bounded buffer problem, or producer-consumer, readers and writers problems, and the dining philosophers problem, which is kind of fun. So what is the bounded buffer problem? We've got n buffers, each can hold one item. We start this with a couple semaphores, both counting and binary. We've got a mutex initialized to the value of 1, meaning it's available. We have full initialized to the value of 0, and empty initialized to the value of n. We're going to use that as a counting semaphore. So the structure of the producer process is we wait until the queue is empty. We wait until this mutex is available. The reason we have these nested mutexes is because the inner one protects us when we write data to the buffer. The outer one protects us from overproducing for our buffer. Okay, that's the difference. That's when we need two. So in the consumer, we wait until the buffer is full. And again, we have the mutex that when we modify our buffer. And when we're done, we signal the empty queue so it can start pushing back stuff. Now, if you notice here, we say that we're signaling that we're waiting for the room to be empty, room to be in the queue. Here we're signaling that something's in the queue, which will then allow this guy to go through, and then this guy will reset the queue, and so forth and so on. Okay, this is a very classic problem, and semaphores are used usually to solve it. I'm going to reiterate, in most modern programming languages, you don't have to come down to this level. There are higher level constructs that make shared sections much easier. In .NET, there's lock. There's also concurrent collections, which are collections like lists that ensure that you don't write to the same area, or that there's no reentry problems. Okay, so the reader-writer problem is a data set is shared among a number of processes. Readers only read the data set. They don't perform any updates. Writers can both read and write. Now, we want to allow multiple readers to read at the same time, but only one single writer can access the shared data at the same time. There's variations of this use sometime, but the shared data is this. You've got a shared data set, you've got a semaphore, the read-write mutex, we've got another mutex, and then we've got an integer count, a read count. So here's a process of a writer process. We wait until we're allowed to write, writing is performed, and then we signal that we're done writing. Okay, now the little trickier one is the reader process. We wait until we have a mutex, till this section is no longer critical. We increment the read count. If it is 1, we wait on the read-write mutex. When we read it, when it's done, we signal the mutex to say, okay, now someone else can read from it, can use it. We do our reading, because basically, remember, we just want to ensure that multiple processes can't come in here while they're writing. Reading is performed. We then wait on the mutex again. We change our count and keep it safe, and then we free the mutex. Again, the point to note here is that we capture and protect every piece of critical data. We protect the attempt to call read and write, and we protect the count variable when we modify it. Now, the thing about it to always remember is this is cross-process or cross-thread. So you shouldn't think of this as this one program running while another one's doing something in your same program. They wouldn't interact, but you're using shared memory and either threads or processes, so they are shared. There are variations. Another variation is the no readers ever kept waiting unless the writer has permission to use the object. or once a writer's ready, it writes as fast as it can. However, these both have the potential for starvation, and that leads to even more variance in approaches. At some systems, it's solved at the kernel level, providing reader and writer locks. Now, again, the thing is, you can run into starvation, which is one process gets stuck waiting for another to free it up, and that is a classically hard problem in computer science to deal with. So, last we have the dining philosopher problem. So, 5 philosophers spend their lives doing 2 things: meditating and eating. That's all they do. They don't interact with their neighbors except when they occasionally try to pick up 2 chopsticks, one at a time, to eat from the bowl. Okay, so they need both to eat, and then they need to release them when they're done. But you can grab one chopstick, and if you can't get the other, you can't eat. So as you see, with 5 people around this, there is the possibility that, for example, number 1 here could grab the chopstick, right? And this guy could grab the chopstick, and this guy could grab the chopstick, and this guy could grab the chopstick, and no one ever gets to eat because they're all holding one chopstick. So we have to deal with cooperating processes. So we've got a bowl of rice, which is our data set, and a chopstick semaphore. So here's the structure of the problem. We've got 5 chopsticks. We wait on a chopstick, and we wait on its other side, and then we eat. Then we release the 2 chopsticks, and then we can go ahead and think. Okay, but this algorithm has problems. is what if things get grabbed between the weights, and you could end up in a deadlock situation. So using monitors, here's a different solution. We've got thinking, hungry, and eating, and we're going to use monitors. Okay, we're going to pick up a chopstick. We're going to have a pickup method and a put down method. In the pickup method, we're going to set our state to hungry. We're going to test to see if our monitor is available, and if the state of that chopstick is not eating, we're going to wait for it. Or the state of that user not using it, we're going to wait for it. Similarly, when we put down our chopstick, we'll set our state to thinking, and then we're going to test the left and right neighbor to ensure they get to it. Test basically says if it's not eating and the current state is hungry, and the next state is not eating and the current state, then we set the state to eating. So basically, if we can get the current chopstick and it's not eating, if we can get the other chopstick and if it's not eating, we're going to, and it's hungry, because remember, the chopstick could be wrapped around, meaning you're the first guy and the 5th guy is the one you're dealing with. That's why you use the mod. If that state is hungry on you, then, and the state of the guy next to you is eating, then we're going to make the state of our guy eating, and we're going to signal that we are better prepared, are able to eat. So we initialize everything to eating. And so a way to look at this, it's kind of hard to explain this, but each philosopher I invokes the operation pick up and put down in the following sequence. Pick up I, eat, put down. No deadlock, but you can have starvation. So sometimes we have a single resource and we want to use a monitor to allocate it. We will use a Boolean, the busy, in a condition Q. A condition, remember, is used for a monitor. And acquire, we're basically going to say if busy, we're going to wait, and when we are allowed to wait, and time is usually a timeout, we will say busy is true, so that way nobody else can get in. And when we release, we set the busy's false, and then we signal that we're done. And basically, remember, this is a monitor, not a class, so basically it will wait on it, and when it's done, let's return to the dining philosopher's problem and talk about it in C#. Here's an actual implementation. Okay. Run is my entry point. I'm using a driver program, so run is like main. So first what we're going to do is we're going to construct all our philosophers and our chopsticks. All right. So here we create a new list of chopsticks, of size 5, and we could run this for bigger if we want. And then we're going to, for each of the philosophers, add a new philosopher to the list of philosophers, and with the number I being the index of that philosopher. Now we're going to run through, and for each philosopher, we're going to set it to the left philosopher's right chopstick. And this is here to trap it if it's null, but it probably won't. It shouldn't ever happen. And do the same with the other right chopstick. with the right chopstick. Sorry. So this basically sets up our program and gets it going. All right. Then we come back to here. We let you know dinner's starting. We create a set of threads, one thread for each philosopher. So here we go. For each philosopher, we create a thread pointing to its eat all method, which we'll go into in a sec. We're going to add it to our list we're going to add to our list of philosophers. And then we're going to take that current thread and start it. So when this is all done, we'll have started 5 philosophers. Now, wait for all philosophers to finish eating basically is the join basically just says wait here till we're all done. Let's take a look at the philosophers then. So here's the philosopher object. Times to eat are 5. We want them to only eat 5 times. We have a list that we pass in of all the other philosophers, so we have a complete list of them, and the current index, and our current number of times eaten for each philosopher. All right, so when we come into the constructor, we just set up everything, and we set our state initially to thinking. All right, and then we declare our public variables that are exposed, and declare a left philosopher method. Well, if the index is 0, then we're going to get 1 from the last. That's a C# notation to say get 1 from the last. Otherwise, we're going to get the current index minus 1. For the right, similarly, if we are at 1 less, we're going to get the first one. Otherwise, we'll get the current index plus 1. So, eat all. It's our main activity, right? While times eaten is less than times to eat. In other words, if we still have turns to eat coming, we're going to eat, and then we're going to put down our left and right chopsticks. So let's look at eat. Eat, we just set the status to eating, and then we increase the number of times we've eaten. It's a bookkeeping. But I'm sorry, I skipped a line. First, we pick up. That's the important part. We're going to see if we can enter the left chopstick monitor. In other words, is it available? We pick it up, and now we're going to try to pick up the right. But if we can't, we're going to wait here. And if we pick up the right chopstick, then both are required, and we return true, in which case we can say we've eaten, and then we put down the left and the right. But if we couldn't get the right chopstick, we're going to put down the left one. So we're not going to be greedy. And if we could not acquire chopsticks, we're going to return false, so we come through and try again. Okay. And all put down left does is it exits the monitor to basically say, okay, we're available, and put down right does the same thing. And think just sets the state to thinking. Okay, so this is a pretty clean implementation, pretty straightforward. And if we run it, we will see the output. Sorry, put in another screen. Where basically, let me get to the top. It starts running through, and various people start grabbing left chopsticks and right chopsticks, and they pick up and put down in a method that lets all the people get through it. So here, we process 2 picks up the left chopstick, and it picks up the right chopstick so we can eat. process 1 picks up the left chopstick, and then it puts it down because it can't get the right one. And so forth. We go through and we execute the algorithm. All kept safe by the various locks. You will be allowed to proceed.